All right. Good morning, everyone. Welcome to our COR seminar series. Today, it's a great honor to have Dr. Ruiwei Jiang from University of Michigan to present his work. He is an assistant professor at Department of Industry and Operations Engineering. He received his PhD from University of Florida and his bachelor from Tsinghua University, China. Before joining University of Michigan, he also spent 2 years at the University of Arizona. And his research is basically in the field of stochastic programming, robust optimization, and integer programming with applications in power systems resilience, and recently in healthcare operations management. His research has been well recognized in many areas. He has won best student paper for the Informs George Nicholson Best Student Award, and also Stochastic Programming Society Best Student Paper, and also won 2 awards for the Informs Junior Faculty Group, Junior Faculty Interest Group Award. And his research has been also funded by NSF. He received his Korea funding award from NSF last year. So he has been well established. Today, he will be talking about nurse staffing under absenteeism, a distribution robust optimization approach. Thank you very much. It's a great honor to have you here, Dr. Ruiwei.
Thank you. Thanks, Ron, for the very kind introduction. It's my great honor to talk in the SEAOR seminar series in GMU. So as Ran introduced, today I'm going to share with you some recent work by myself and by my co-author, Min-Seok Ryu, who is my previous PhD student in Michigan. He has now moved to the Argonne National Lab. So the nurse staffing is the interest of is the study of interest today for us, and nurse staffing is significant in the healthcare industry. So partly because it has a large expense. So in here, this is then a pie chart about how hospitals spend their money on salary. So the nurse staffing cost actually takes up as large as 30% of that salary expenses. So that's significant. So from that perspective, one might think, okay, so maybe from a lean management perspective, it would be better to save some staffing costs by reducing the number of nurses with staff. Unfortunately, that's not a very good idea because nurse staffing is linked to another key performance metric in hospital management, which is the patient safety and the quality of care. So less staffing means less safety for patient care, and so for that reason, a lot of governing agencies, including those in Canada and in US, recommended such a nurse to patient ratio or NPR. To guarantee that we could maintain certain level of service in terms of nurse staffing. So in here, you can see like different units could have different recommended NPRs. One patient, one nurse is corresponding to 2 or 3, in some cases, more patients. So nurse staffing typically consists of the following 4 phases. Depending on different timelines, timestamps that would take place. So phase number 1 is the demand forecasting and staffing, which typically take place months ahead of the shift actually takes place. So in this phase, the hospital managers will make some prediction of the upcoming nurse demand in that particular shift, and accordingly make a staffing decision. So this staffing decision is only about the number of nurses, right? So how many of nurses do we need in that particular units, in that particular and in that particular shift? So it has nothing to do with like who to put there, and then how to respect their own preferences or working pattern. Phase number 2 is that take place like weeks ahead of the shift takes place. So it's called the nurse shift scheduling. So this second phase is about like scheduling individual nurse and then respecting their own like working pattern and working preferences. Phase number 3 takes place days or 2 hours ahead of the shift. It's called the pre-shift staffing and rescheduling. And it's typically used to hedge against certain uncertainty that should arise in the working pattern of the shift. And so for many reasons, including like family obligation, weather reasons, holiday effects, the number of nurses that actually show up for the duty could be lower than the staffing level. Say we staff like 10 nurses for that particular shift in particular day, but maybe only 8 of them will show up. This is a so-called nurse absenteeism phenomenon. And as I said, that there could be like multiple factors that contributing into such a nurse absenteeism. But a study in the empirical research of this area, the number of nurses we staff for that shift is the major driving factor for such nurse absenteeism. So it could be like the number of nurses we staff for that shift is like less than sufficient. Then in that case, some nurses could tend to not show up because of the expected higher workload. The final phase is the nurse-patient assignment, and it typically happens like hours ahead of the shift takes place. So in that phase, we would kind of connect each single nurse to like 2 or 3 patients according to the NPR, according to the nurse-to-patient ratio recommendation. So along the timeline, there are like 4 phases of nurse staffing taking place. The shift actually takes place. In our study, we look at phases number 1 and number 3. So the staffing and the pre-shift staffing. So that means our study is only about like deciding the number of nurses, the level of staffing. We don't look at like the working pattern or the preferences of each individual nurses. Those will be decided in phase 2 and 4, which is out of scope of our consideration. But nevertheless, the output from our research can be seen as an input to the phases number 2 and number 4 to help make this more detailed scheduling or nurse-to-patient assignment decision. Okay, so although we are only interested in a number of nurses to staff, this problem could nevertheless be challenging due to the underlying uncertainty. So this uncertainty could come from both demand side and supply side. From demand side, the nurse demand could be uncertain, typically due to random patients' census. And this is the so-called exogenous uncertainty, because whatever our staffing decision is, probably not going to impact how many patients that will show up. That's the kind of a given or exogenous uncertainty. On the other hand, the nurse absenteeism comes from the supply side. The nurse absenteeism could create such work-related stress, which put us in this quote-unquote vicious cycle. So you could imagine the following scenario that if the less number of nurses show up for work, then the average or expected amount of workload will increase among those nurses who do show up. And the higher workload would increasingly encourage those nurses to not show up for their future assignments, and that will further decreases the number of nurses showing up in the future. So this cycle will go on, and eventually leading to like a less number of nurses showing up for work, and then hence like a lower level of patient care. Well, so different from the nurse demand uncertainty, such uncertain nurse absenteeism could actually depend on the staffing level, as we mentioned just now in this vicious cycle. So for that reason, this uncertainty is actually a decision-dependent uncertainty. In other words, it's then kind of an endogenous uncertainty defined in the literature. So to hedge against that, maintain the safe nurse-to-patient ratio, typically the hospital managers will need to call in some so-called temporary nurses to maintain the patient safety and quality of care. Well, those temp nurses could come from, say, the regular nurses we staff and do show up in the previous shift. They for some future shifts that is short of nurses, or we could call in some agency nurses that hospital have a contract with. So more on the nurse absenteeism. So we look at the data from a unit in our collaborating hospital. So we collect data for several years, and those data could looking like attendance records of nurses, right? So we could have like a pair of data showing the number of nurses we staff and the number of nurses who do show up for their duty. So that leads to this kind of a dot graph we're showing here. The x-axis is the staffing level or in that unit. So how many nurses we staff in phase number 1. And the y-axis is the number of nurses who do show up, who actually show up in phase number 3. So the dot here represents a historical data sample. So for example, in here, you could see this dot with coordinates 14 and 11. That means we staff 14 nurses to in that unit for shift, and eventually 11 of them show up. Okay, and the dot size represents the data frequency. So the larger the dot is, the more frequent that data sample will take place in our data record. And we also do some simple statistics. We compute the kind of average number of nurses who show up according to the staffing level. That leads to this red curve, the zigzagging red curve that you see in the graph. So that tells you that indeed the number of nurses that show up depends on the decision, the staffing level of nurses in that unit. Well, we could look into more details about that. This time we generate a different graph using a different y-axis. So the data is the same, the x-axis is the same, but this time we use a different y-axis representing the show up rates, meaning that we divide the number of nurses who do show up by the number of nurses we staff. And as you can see, the show up rates in the y-axis here is somewhere in between 65% to 90%. So that's kind of the general show up rates for the nurses we staff. And we also make this red curve to represent the expected show up rates versus the staffing level. As you can see here, under different staffing level, we do have a different show up rates. So the possibility or the probability of a nurse showing up for work is actually significantly depending on how many nurses we actually staff. So depending on the staffing decision we make in the first place. And interestingly, you can also see a decreasing trend of that red curve. Intuitively, that means the more nurses you show up, it kind of showing up this trend that the less likely the nurses will show up for work. Okay, so that's on the so-called endogenous uncertainty of such random nurse absenteeism. So in addition to hiring such temp nurses to make up for the NPR, another approach taken by many hospitals in practice, including our collaborating hospital, is to use the so-called float pool of nurses. So what float pool or simply pool means, it's a group of units or wards. So we put like several units together to form a pool. For example, if we have 4 units with say similar functionality, then we can pool all of them into one single pool. And in a different example, we could decide to pool like different units, different subset of units into a pool. For example, units 1 and 2 will form a pool number 1, and unit 3 and 4 form a second pool. So how do those pool works is as follows. So instead of directly staff the nurses into each single unit, we would staff some nurses to the pool that is formed by subset of units. So taking this, for example, if we have some nurses in pool number 1 and some nurses in pool number 2, then in phase number 3, after I realized, like, how many nurses are actually showing up for their work, maybe I find out that some units are short of nurses. In that case, I can so pre-shift, I can assign some pool nurses to make up for the shortage of nurses in those units within the pool. So the pool nurses are assigned to a unit within the pool after the uncertainty are realized. And certainly that would help to increase the operational flexibility because we can kind of delay a part of our staffing decision essentially after the uncertainty is revealed. Right, so how many nurses are actually showing up, and that could, of course, help to reduce the number of temp nurses we need to hire, and furthermore, that lead to like higher quality of care and lowering the nurse staffing cost. Well, the last two bullet points mentioned here, because those temp nurses, it's not only like expensive to hire in terms of salary, it's also because their care, their quality of care, and familiarity of the workload in each unit is actually at a lower level as compared to either regular nurses who would staff in the units, or the pool nurses who would staff in the units in phase number 3. So if you factor in this, the quality of care the temp nurses could provide, the hiring temp nurses is actually quite a costly option to use. So that's why we, many hospitals that are considering this option of floating pools to help increase the operational flexibility and reducing the number of, reducing the hiring of temp nurses. Okay, so in terms of the flow pool structure, so we can see that the level of flexibility brought about by the different pool is different as well. In here we mentioned there's 2 examples. The first example, pulling all the 4 units into the same pool. This is so-called the one pool structure. And this is arguably the most flexible structure, because any nurses you put into that one single pool will be able to work in any of the 4 units within that pool. Right. So in contrast, the second example is less flexible, because the nurses you put into, for example, pool number 1 can only be assigned to use in unit number 1 and unit number 2. They can now be assigned to unit 3 and 4. That's a lower level of operational flexibility. But on the flip side, if you want more operational flexibility, you need to cross-train the nurses a lot, right? So those nurse you assign to this one pool structure, for example, need to be cross-trained for all the 4 units, meaning that pool nurse need to have the skills to work in any of the any units in that one pool structure. So different pool structure leading to different level of operational flexibility, but that actually also leads to the more number of cross-training. So an interesting question to consider in this case would then be, to minimize the total amount of cross-training needed in order to obtain certain level of operational flexibility, but also leading to an optimal kind of pool structure design. Okay, so a very brief literature review. So the majority of the literature focused on deterministic model, meaning that those models will just ignore, both uncertainty, demand uncertainty, and absenteeism uncertainty. Typically, that leads to an underestimate staffing cost by this reference number 5. So a different group of model is called the stochastic programming model. So, within that stream of research, majority of papers focused on demand uncertainty, while ignoring absenteeism uncertainty. According to the reference number 4, such models could result in understaffing. Well, in here, understaffing meaning that we are staffing like insufficient number of regular nurses and pool nurses, and that means we typically we need to hire more temp nurses. Then that lead to like higher total staffing cost and lower the quality of care. If we do want to consider absenteeism uncertainty, which is endogenous, then we need to immediately we kind of hit a wall of computational challenges. That is those kind of endogenous uncertainty model is described as computationally prohibitive by reference number 6. And in the majority of existing papers, employ heuristic approach to solve such computationally intractable models. So given this challenge, a very intuitive approach to address such computational challenge of endogenous uncertainty is to use this kind of a learn and optimize kind of a heuristic, right? So on the one hand, we have the staffing level to make decision on, and on the other hand, we need to kind of calibrate this probability of nurse being absent, which depends on our staffing decision. Maybe we can, learn and optimize. First, I decide some staffing level. Then, I observe the realizing probability of absenteeism. Then, according to what I observe, I come back to adjust my staffing level. Well, I understand that the probability distribution might change, but how about I do this iteratively? Right? So I make decision, observe the probability, come back to adjust my decision, and so on. So maybe that will lead to certain converging behavior that has some optimality guarantee. Well, unfortunately, that would also lead to understaffing, mentioned in paper number 4. So a potential workaround of this challenge is to use the so-called parametric model, which do take the endogenous uncertainty into account, but assuming that those uncertainty are independent and homogeneous. Right? So, for example, each nurse is assumed to be independently show up or not show up for their duty, and their absenteeism probability distribution is kind of identical. Right? So that could be made a data-driven model by looking at the attendance record of nurses, and even better, this reference number 4 actually come up with a closed-form solution if we are only interested in do like 1 unit of staffing. But it's unclear like how to extend such approach to a multi-unit, multi-pool setting, like in our paper. And I guess that the second important question is that what if this chosen kind of parametric model is biased, right? So how to calibrate our model to hedge against such biasness of, if our assumption of independence and homogeneity actually fails in practice. So our proposal is to use a non-parametric model. So instead of using this one single distribution that is parametric, we propose to use to look at a family of probability distributions. That means we consider multiple, and in some cases there could be infinite number of distribution, all of which are plausible to model the nurse absenteeism uncertainty, which is endogenous. That will lead to this so-called distributionally robust nurse staffing model, or DRNS for short. So in our setting, we consider this so-called moment-based ambiguity set. In here, ambiguity set means we are considering a family of distribution, and all of such distributions satisfy certain moment condition on the uncertainty. So the moments in terms of nurse demand could include the support of the demand, the mean value, their standard deviation, and so on. For the nurse absenteeism, we could say, the random number of nurses who show up for work is less than or equal to the staffing decision. Right? So this is kind of a support requirement on the absenteeism uncertainty. Also, we can consider the mean of the number of nurses who show up for work, modeling that as a general function of my staffing decision. Okay, so that can also be made data-driven, since we mentioned if we get the attendance record of nurses, we could use that to calibrate such a dependence between the mean value of this endogenous uncertain random variable with our decision variable. Okay, so we do consider multi-unit, multi-pool setting, and the good thing about our model is that in this model, we do not need to resort to heuristics approaches anymore. Actually, as we would show you later, this model can be represented as a mixed integer linear program, which can be solved to global optimality by using commercial solvers. We also extend this model to to address this interesting question of how can I optimally design my pool structure. Okay, so here's a little bit outline for the remainder of the talk. So we would introduce this DRNS model, which is a two-stage distribution robust model with a moment-based ambiguity sets. We're going to recast it as a deterministic two-stage model that facilitates for a design of a specialized separation algorithm for solving such a reformulation. In several special pool structures, we can even find a better, more tractable reformulation, that is the monolithic or one-stage MILP. We also talked about the OPD, the optimal pool design model, and show you some numerical case study. And all the technical details of our reformulation, we relegate them to the end of the talk, if we have time. Okay, so first on to the DRNS model. So as I said, this is a two-stage model. In stage number 1, we make the so-called here and now decision, and that's that takes place like months ahead of the shift actually takes place. This first stage decision consists of 2 variables, so W for the number of nurses we are assigning to unit J, and that's the so-called regular nurses. And a second set of decision variable Y, representing the number of nurses who are assigned to the pool. Okay, so the so-called pool nurses staffing level. So the overall objective function is to minimize the worst case expected total staffing cost. Well, in here, total staffing cost consists of 3 parts, as highlighted over here. We have the cost of regular nurses, the cost of hiring pool nurses, and the expected cost of hiring temp nurses. Well, the temp nurses are put into this expected operator because temp nurses is decided in the stage number 2 of this model, right? So we decide like how many temp nurses to hire after we observe like how many nurses are actually showing up for work and how many nurses are demanded in that particular shift. So for that reason, temp nurses cost is put in an expected value form, and more importantly, we are looking for the worst case expected value for all possible distribution P of the nurse absenteeism and nurse demand within that ambiguity set, which we denote by this curly D notation. So in here, there's a little bit of notation we need to distinguish. So W here is the W and Y here are our decision variables. And since the nurse could be absent for work, so we used an accompanying set of notation, W tilde and Y tilde, to represent the random number of nurses who actually show up in the units and in the pool, respectively. So tilde here means the uncertain number of nurses showing up. So finally, eta tilde here represents the nurse demand. So this exogenous uncertainty. And this is our design of the ambiguity set. So we are considering this all such distribution that will satisfy the 3 conditions we describe over here mathematically. So the first set of constraints is for the exogenous nurse demand uncertainty. More particular, we consider the marginal moment information of that random demand. So for each random variable eta tilde, we raise it to the power Q. So we are considering the Q's moment of this nurse demand. We require that the mean value of that nurse demand to be matching mu JQ. So the average moment data we obtain from our patient's census data set. The second set of conditions in the ambiguity set is about the nurse absenteeism. So more specifically, we require that the mean value of the number of nurses who show up for work depends on the decision, staffing decision we make. So the random variable W tilde its mean value is going to depend on my staffing level W with a general function, which we call Fj. So this F function can be calibrated by using the attendance data record for the nurses. And in general, F is the piecewise linear function. Similarly, for the pool nurses Y tilde, we can model its mean value as a general function G of my staffing decision Y. Okay, so that's our the design of our ambiguity sets, a moment-based set of probability distribution. So more onto the calibration of sets, right? So this is the graph we showed you before. So the number of nurses who actually show up depends on the staffing level decision. So according to the data attendance record of nurses, we will be able to come up with this red curve in the graph, which represents the average number of nurses show up as a function of the staffing level decision. So that's how we are going to calibrate the ambiguity sets. All right, so onto the second stage model of the DRNS. So as I said, in the second stage model, we need to decide like how many temp nurses to hire. Well, so the physics or the dynamic of this second stage model looks like this. We wish to minimize the total cost of hiring temp nurses. So what we do can be explained by this example. Suppose that we have 4 units. We group the first 2 units into pool number 1, the last 2 units into pool number 2. At the beginning of this second stage model, we first observe like how many nurses are actually showing up in my 2 pools and all of my 4 units, denoted by Y tilde and W tilde. Right? So after observing that, we can now assign my pool nurses into those units represented by this decision variable Z. Right? And after which, if some units are still in short of nurses, then we have to call in some temp nurses represented by decision variable X to make up for the safety NPR, the nurse to patient ratio in those units in shortage of nurses. So this dynamic can actually be modeled by using a mean cost flow formulation, so which we won't bother you over here. So basically the second stage formulation for our model is the mean cost flow. All right, so putting all the things together. So this is a 2-stage model with endogenous ambiguity sets. We are interested in minimizing the total staffing cost with regard to the worst case probability distribution that can be picked adversarially from an ambiguity sets that further depends on the staffing decision we make in terms of regular nurses and pool nurses. So we are able to recast such a model into a deterministic 2-stage formulation. And since it's a deterministic formulation, we'll be used a separation approach, separation algorithm to solve that 2-stage reformulation into global optimality. So for more special pool structures, we can actually make the reformulation a little bit more computational tractable. Actually, for the 3 special pool structure we consider, we can reformulate the DRNS model into a 1-stage, the single level mixed integer linear program. So those in here we are considered 3 special structures that typically that are typically adopted in practice. So the first structure over here is the so-called 1 pool structure that we already introduced. So in this structure, we have like 1 single pool governing all the units, right? So that's this is kind of the highest level of operational flexibility. But on the flip side, we need to like cross-train the many number of units. The second type of units. The second pool structure is over here, what we call the disjoint pool structure. So in the structure D, we could have multiple multiple pools, but each pool will be governing a disjoint subset of units, right? So we could have like a pool number 1 governing only unit number 1, and pool number 2 governing units 2 and 3. So different subset of units belongs to different pools. The third structure is the so-called train pool structure, structure C. So this concept is inspired by this long train structure used in the manufacturing flexibility industry. So so in this structure, like each pool will be governing 2 units and 2 units only. And each unit will be governed by 2 pools and 2 pools only. So, any 2 neighboring units, they will be sharing actually 1 pool. Yeah, so for this three special pool structure, we can make the reformulation a little bit more tractable. This is a kind of a single MILP that we need to solve, and that could be directly solved in commercial solvers. Okay, so on to some computational results. So first, the data and instance design. So we look at 5 units of data from our collaborating hospital. So we collect like the data from like July 2010 to June 2014, roughly 5 years. So the format of data looks like this. In each row represents a data record. The data record includes the random demands of nurses in those 5 units, and also the attendance records in those 5 units as well. So, number of nurses with staff versus the number of nurses who actually show up. We use the data to design the instance by doing the splitting of data. We use like 80% of the data for training, including calibrating our ambiguity set and solving the DRNS model, and the remaining 20% of data for out-of-sample testing, right? So eventually we are going to expose whatever decision we make in the model to those 20% of out-of-sample data, and then see how the solution actually perform in those data that the solution haven't seen before. All right, so in the computational result, we try to answer a series of questions. The first question is that why DRNS, right? So why distribution robust model? Since we have the data, we could have adopted a different stochastic programming kind of model, right? So instead of modeling this W tilde J, the random number of nurses show up as a kind of a general function of my decision variable, I could more directly say, W tilde is this show up rates P times multiply with my staffing level W, right? So wouldn't that be more straightforward to use in the stochastic programming model? Right? So we could similarly do the same thing for the pool nurses, the Y tilde random variable. Well, we do a comparison out of sample, right? So we solve the stochastic programming model and the DRNS model to optimality. We obtain this 2 solution. We then expose both solutions to the same set of out-of-sample data, those 20% of the data we got. And then we compute the average total staffing cost, including the cost of hiring temp nurses, and compare how these 2 solutions perform. As you can see in the table, so these 2 columns represents the actual total average staffing costs according to the data. And in here we have kind of a gap comparison in between these 2 different performance. Positive number of gaps over here represent the better performance of the DRNS model. And sometimes the gap could be like significant. And we have different gaps, by the way, under different nurse pool structure. Structure 0 here represents no pools. So all the units will work by their own. There's no pools designed to increase the operational structure, to increase the operational flexibility. Structure 1 is the one pool structure. D is the disjoint pool structure. C is the train pool structure, and we have some kind of randomly generated arbitrary pool structure. And yeah, so those are like gaps in between the DRO model and the SP model underneath the different pool structures. So we also record the average number of temp nurses hired in both the optimal solution. And as you can see here, typically the DRO model will hire less number of temp nurses as compared to the SP approach. We also look into the optimal solution of the SP model and the DRO model to try find the reasoning of why there's a performance difference. So the intuition here is that the SP model, the SP optimal solution, actually hires more regular nurses. In contrast, the DRO model hires less number of regular nurses and put some more investment into hiring the pool nurses in order to increasing the operational flexibility. Well, and that actually explains the performance difference in between these 2 approaches, because if you still remember the previous kind of a curve I show you, the show up rates, the probability of a nurse showing up for work is actually decreasing as the number of staffing level increases. That means like more nurses more regular nurses I staff, actually less likely an average nurse will show up for work in that unit. Right? So the DRL model, because it does consider this endogeneity of my nurse absenteeism uncertainty, it takes advantage of this understanding that if I staff more, then less likely on average people will show up. So it strategically decides to staff less number of regular nurses and put more investment into the operational flexibility by hiring pool nurses. The stochastic programming model, on the other hand, because basically it ignores this nurse absenteeism, it wouldn't be able to take advantage of such understanding from the data. Okay, so the second question is that, why am I interested in modeling the absenteeism? I can ignore the absenteeism in my DRNS model and still come up with a DRL solution. How does modeling absenteeism bias? Okay, so to that end, we solved two DRNS models, one considering the absenteeism, the other ignoring it. Right? So we similarly compare them in an out-of-sample testing. And as you can see over here, right? So the performance of the model considering absenteeism is much better. So in here we have this curve of comparing the average staffing cost with the DRNS model, ignoring uncertainty in the x-axis versus the considering uncertainty shown in the y-axis. Right? And the dots here represents the out-of-sample the cost comparison of these two models. We have this 45-degree line to represent the case that this two model generates the same equally good performance. But as you can see, most dots are lying like underneath this 45-degree curve, meaning that the staffing cost of the DRL solution that ignores the absenteeism uncertainty actually leading to a higher staffing cost. The similar observation can be made in terms of the average number of temp nurses we hire in these two models. Okay, so some motivation of using the OPD model. So we've already talked about this optimal pool design, with regard to different level of operation flexibility with the number of cross-training. We can see that more straightforwardly in this example. So the same, these two different pool structure actually leads to the same the staffing cost output by the DRNS model, but they have a very different number of cross-training. So that motivates us to minimize the number of cross-training, subject to a constraint that we have some target distribution robust staffing cost. So that's how we design our OPD model. We try to minimize the number of cross-training, subject to this additional constraint that I have a cap on the staffing cost. So indeed, we can observe that increasing the target staffing cost leads to like a less number of cross-training. So in this graph, I'm actually changing the target staffing cost from the one pool structure to the zero pool structure. Right? So one pool structure is the highest level of operational flexibility. So it's the target. So it's the staffing cost should be the lowest. On the other hand, like no pool structure is leads to the highest staffing cost. So we kind of sweep the target cost in between these two extremes of the spectrum, and then see how the number of cross-training changes. Right. So indeed, the number of cross-training will decrease if we allow a higher and higher like ceiling on the staffing cost. But as we can see, like even if we require the lowest, the tightest target staffing cost, we need like need only as many as like 4 cross-training to obtain that target staffing cost. Meaning that using a very low number of cross-training, we can already harvest the almost all of the operational flexibility. Okay, so that leads us to the next question. So which units do we actually pull together? Right. So in an instance, we could have the units with the very different level of variability. right? So in some units, we could have like high variability in terms of demands, a low variability in terms of absenteeism. In some other units, I could have the flip case. So which units do I pull together in the optimal pool design structure? Okay, so to that end, we kind of split all my units into 4 categories. So according to the high or low variability of demand uncertainty and nurse absenteeism uncertainty. Okay, and so we would label all the units with high variability as A, and all the units with low variability as the unit B. And we consider the following 3 cases in the LPD model. Case number 1, I consider only random nurse demand, and I don't allow any absenteeism to take place. Case number 2, is the flip side. I don't consider any, I don't allow any nurse demand uncertainty, or the demand is deterministic, but I allow the nurse to be absent. Case number 3 is the mixed case, both random demand and random absenteeism. And then in all of those 3 cases, I solve the LPD model and observe the optimal solution to see that which units am I'm pulling together. So to that end, I also have the 3 types of nurse pools. In type 1, the pool will only pull together those units with higher variability. Type 2 pools is for the pool with only like low variability units. And type 3 is the kind of the mix. In the pool, I have some units with high variability. I have some other units with lower variability. Okay, so in each of those 3 cases, I'm going to examine the characteristics of my optimal solution of pool structure, and to understand like which units I'm actually putting together. Here's the results. So in each case number 1, number 2, and number 3, I observe my optimal solution and do a statistics of how many type 1 pool do I observe, how many type 2 pools do I observe, and how many type 3 pools do I observe. Okay, so in case number 1, in which the nurses only have demand uncertainty, but no absenteeism whatsoever. As we can observe from this histogram, actually the most pools, a majority of flow pools are kind of a mixed pools. So in the pool, there are like some units with higher variability and some units with lower variability. Things change very dramatically as soon as we move to incorporate nurse absenteeism uncertainty. So in case number 2 and case number 3, I allow the nurse absenteeism to take place. And then in that case, when I solve the LPD model, surprisingly, I find out that most of the pools I observe in the optimal solution are type 1 pools, meaning that in those pools, those are only the units with higher variability. So I'm essentially pulling together all those units with higher variability of demand and higher variability in terms of nurse absenteeism. Okay, so that's the intuition we got here. So units with higher variability are grouped together. Type 1 pool are observed like almost always as soon as we incorporate the nurse absenteeism uncertainty. Okay, and if you compare cases 1, 2, and 3, we observe that the nurse absenteeism actually plays a more important role in the pool in the optimal pooling strategy as compared to the nurse demand uncertainty. Okay. All right, so the last part, if I still have several minutes, I would like to mention a little bit about the technical details of how we reformulate and solve our DRNS model. So this is the recourse or second stage model that I talked to you previously. That is min cost flow. The formulation is over here. So in order to solve this DRNS model, we first need to take a due of this min cost flow model, and then obtain this due problem, which I have due decision variables alpha and beta living into a due feasible region, which I call capital lambda. Okay, and then I will be able to recast my worst case expected value in the DRNS model by using this min max model. So this is a kind of a 2-level 2-stage model I optimized some dual variable in the outer minimization loop. And in the second stage, I need to optimize over my dual variable alpha and beta, living in this polyhedron lambda. And I need to maximize this function f of alpha and beta. Okay, so this function f is actually, the detail is over here, but if you take a closer look, you find out that this capital F function is actually a convex function in terms of alpha and beta. So in other words, in the reformulation of our DRNS model, we need to solve this convex maximization problem, which is just in general NP hard. Okay, so what can we do? Well, we know that in order to maximize the convex function, all we need to do is to check the extreme points of the underlying feasible region. So that's what we do. We first look at the feasible region of alpha and beta, and then characterize some property of the value of alpha and beta in the extreme points, summarized in the theorem. Then we hire some new binary variable to encode the value of alpha and beta in each and every of the extreme points of the feasible region. So instead of using alpha and beta, I now can use binary variable to indicate like which extreme point I'm visiting in this convex maximization problem. Okay, and because of this binary encoding, I'm now able to rewrite this convex maximization problem, not as a continuous problem anymore, but as an integer program, as an IP problem. Okay, so and that leads to a separation approach of solving this general DRNS model, in which we can, optimize an IP problem as a subproblem, and then separate over the epigraph of this max f function in the higher level problem. Okay, so by using this separation approach, we will be able to solve the DRNS model to global optimality. So for the special pool structures, we can get more tractable reformulations. And the reasons for doing that is luckily, it happens that in those special pool structure, when I'm trying to solve this integer program subproblem, that subproblem suddenly becomes a linear program, which I can solve within polynomial time. And even better, I can take the dual and merge this LP into the higher level problem. Okay, and yeah, so as I mentioned, in the first two structures, one pool structure and this joint pool structure, we find out that the feasible region of the IP subproblem, which I call H, is actually the convex solve itself. So if we simply relax the integrality restriction in the IP problem, we get an LP problem that is equivalent to the original IP. For the third structure, the chain pool structure, actually things are not so perfect. So if you relax the integratory restriction, that LP relaxation no longer give you the convex solve. But nevertheless, we will be able to recast that IP subproblem as a longest path problem on an acyclic graph with polynomial size of nodes and arcs. That means this IP problem can still be solved in polynomial time. And because of the longest path problem structure, we will still be able to rewrite that IP problem as an LP. And so similarly, we can take the dual, merge that into the higher level problem, leading to a one single level of mixed integer linear program to solve in the DRNS model, underneath the special pool structures, of course. Okay, so I guess that's it. I think I only have like 6 minutes left, and with this, to open up for questions and to this paper link on arXiv. And I want to thank you for your attention.
Thank you very much. Thank you very much again, Yuri Wei. Let's now open the floor for questions. If there's any questions from the audience, you can open your microphone and speak, or you can type your questions in the chat box. We can handle it as well.
I had one question about sort of the relationship between the staffing level and the absenteeism rate. So the higher the staffing level, the greater the absenteeism rate, right? And so how does that, you also mentioned kind of a feedback loop where where, you know, if there's not enough nurses staffed, that they sort of see that and they see they're going to have a, you know, higher workload, and so then they avoid coming in. So it seems like that would suggest a lower, if you have a lower staffing level, that would yield a higher absenteeism rate. So, what's the relationship between those two?
Yeah, so the curve I showed you previously is summarized from the data we get from our collaborating hospital. So we do see a lower, a decreasing trend of the show up rate as the staffing level increases. That's somewhat different from what we found from the conclusion of other empirical papers. So what they mentioned is that you know, the higher staffing level, the higher staffing level, the higher the show up rate would be. So we are kind of surprised to find out a different conclusion from the empirical data from we obtained from our collaborating hospital. But indeed, we also understand that different cases could happen in different hospitals and even in different units and every like individual nurses. So so in the empirical study, different cases could show up. Like you know, sometimes you could see an increasing trend, sometimes you could see a decreasing trend, and sometimes the show up rate doesn't change actually for lots in terms of different staffing level.
Thanks. Okay, so it's the data that, so in the particular data that you observed, it didn't necessarily coincide with you know, sort of modeled theory. Thanks.
Yeah, so different models actually, different data actually suggest different impacts of staffing level on the show up rate. So it just happens that in our particular case, for the data we can obtain, we see the decreasing trend of show up rates.
Okay, thank you very much. Is there any other question? So, I have one question regarding the description for this endogenous uncertainty. So
sure.
When you learn this relationship between this decision and the decision-dependent uncertainty there, how sensitive is this endogenous uncertainty to this coupling function or this linking function there, which you use as a linear approximation function, linear piecewise function?
Yes, yes. So yeah. So the curve is shown here. I'm not sure if you can see my cursor. Like yes. It's on the lab panel figure. Yeah, so the sensitivity is reflected over here. And so it might be not so straightforward to see how sensitive it is, but if you turn to the show up rates, as you can see, like as we increase the staffing level, say from 12 to 16, the show up rate could drop from like around 80% to like around 60%. So yeah, so I would say that's a pretty significant change in terms of, you know, this endogeneity. And yeah, so, and this is also reflected in our later like computational study of like, you know, considering or ignoring the absenteeism. Yes.
Thank you. Is there any other questions here? Well, I think we are just about on time. It's about noon now. So thank you very much for everyone. Let's give a applause to Dr. Rui Wei for his nice presentation and for this seminar here today. And if you have any questions, please let us know. And I will be posting this video on our SUR YouTube channel there. You can watch the video later. Thank you very much again. And everyone have a good night, nice weekend.
Thank you for attention again, and thank you again for the kind introduction and invitation.
Thank you.
Thank you.
Thank you.